Hi, and welcome to another episode of Spiral Physics Education. So in this lesson we're going to be looking at linking kinetic energy and work done from a mathematical point of view. And we're going to be looking at different types of examples that can come up in exams dealing with work done and kinetic energy. And we're going to be using these two equations that we've covered in different episodes on this topic. So to get the most out from this lesson, what you really need to have is a strong understanding of energy stores and transferred, including examples of each. You also need to know about the principle of conservation of energy, and that work is done when energy is transferred between different stores, and also that kinetic energy can be calculated using this equation, 1/2 times mass times velocity squared, and that mechanical work done could be calculated using work equals force times distance moved in the direction of the force. All of those have been covered in other episodes from my channel. So, kinetic energy and work. Well, let's suppose that kinetic energy increases for some reason. So that kinetic energy store would increase because a force is doing some work on the object. So that's a mechanical transfer of energy isn't being involved. And even if we have a decrease in kinetic energy, then a force is involved, and then for mechanical transfer is being done on the object. So whenever an object's kinetic energy changes, a force must be doing work on that object. That means that we can use this equation here, work is force times distance moved in the direction of the force, when we're dealing with work. And we can also use this equation to calculate the kinetic energy, and that is 1/2 times mass times velocity squared. But because we're dealing with changes in kinetic energy, so if an object's kinetic energy changes, increases or decreases, that's when work is done. So we have to consider this equation where the delta at the beginning means change. So we've got change in kinetic energy equals the final kinetic energy minus the initial kinetic energy. And if that value is bigger than 0, work is done. And if we then substitute in an equation for that, so we've got 1/2 mv squared representing the final kinetic energy of the object, and we're substituting the letter u for the initial velocity, which is done often in physics, especially if you've come across acceleration, which change in velocity over time, or a equals v minus u all over t. So the u here just means the initial velocity, and v means the final velocity. And if you are mathematically confident with this next step, you can see that there's a 1/2 m in both of those parts of the equation. So we can take that out and we can put some brackets around the two squares of the velocities and tidy it up a little bit. But if you're not sure what's happening, it doesn't matter, you can use the other equation, even though it's a little bit longer and more complicated. So we're going to be using all of those equations in the next few examples. So let's start off with an example of a car, and this car is going to start from rest, and it's going to go to 8 meters per second in 25 meters. So we're going to calculate the average force exerted by the engine. And we say average force because we're not sure about the value of the force being constant. So we didn't need to know that, so we can just say on average. So it's not a complicated part of the question. So because we're dealing with changing kinetic energy, we can write this equation down, where we've got final kinetic energy minus initial kinetic energy. But really, I want to draw your attention to this word rest. So whenever you see the word rest in an exam, make sure that you are aware of what that means. So in this case, it deals with the original kinetic energy. It means that originally the kinetic energy was 0. So it's actually telling you a mathematical number in words. And often students forget that and don't deal with the word rest in the equation. So that means our kinetic energy, our change in kinetic energy, is just actually the final kinetic energy, because the initial is 0. So here we can work it out by 1/2 times 1000 times 8 squared, and we've got a change in kinetic energy as 32,000 joules. And that's the first part of the question done. Now we lead on to, if there is a change in kinetic energy, then work must have been done. And that work is done mechanically, so we can use work equals force times distance. But in the question, we're trying to work out force, so we need to rearrange it. The thing is, where's this work bit? Well, we've already calculated it. Work is the change in kinetic energy. So we just substitute in that 32,000 into our equation there, divided by 25 metres. And we get our work done being used to calculate the engine force, which is 1,280 newtons. And that means that we've actually ignored the effects of air resistance and frictions, because it gets a bit more complicated when we have those. Let's have a look at another example. So we're still dealing with the same car. It's moving at 8 metres per second, and it accelerates at 12 metres per second in 50 metres. So that we want to, again, calculate the average force. So it's a little bit more complicated because it's already moving. So we start off with our equation to be able to calculate the difference in kinetic energy. I'm going to simplify that because I prefer to use this equation as it uses less terms in the equation. And now I can substitute in the numbers from the equation using 1,000 for the mass, 12 squared for the final velocity squared, and 8 squared for the initial velocity squared. We get 40,000 joules for that. So now I can substitute now all our values into this equation. We're dealing with the work done by the kinetic energy. So we rearrange that for force because we're dealing with the engine force. And once again, we're dealing with work, and work is just the change in this kinetic energy, the 40,000. So we can substitute that in to our equation and divide it by the 50 metres that it's taken for us to change our speed. And we get that the engine on this occasion, on average, has exerted 800 newtons over that 50 metres. And of course, we're not including air resistance and friction in this question. So let's have a look at a third example, and again we'll just use the same car. So this is now moving at 12 metres per second, and it puts the brakes on. So we're not dealing with the engines doing work, now we're dealing with the brakes doing work. And let's say the brakes are exerting a force of 2,300 newtons. And we're going to calculate how long it takes for the car to come to rest, what we call braking distance. So we're still dealing with this change in kinetic energy, but we've got this word rest involved. But this time, this rest means the final, it's coming to rest. So the final kinetic energy is actually 0, which simplifies our equation a little bit now that we've realised that. So we can substitute in our numbers, 1,000 for mass and 12 squared for our velocity squared, and we get minus 72,000. Don't worry about the minus. It just means that the kinetic energy is decreasing. It means that the force is a decelerating force. It's just telling us other stuff. So actually we can ignore it now. And now that we know how much work is done, this 72,000 joules, we can use our equation, work is force times distance. We can rearrange it, so we want to work out the braking distance, so rearrange it for distance equals work done over force, and that 72,000 is the work that we have done and calculated using kinetic energy. And we get an answer of 31 metres, and we've just done that to 2 significant figures. So I hope you found that useful and working out work done and kinetic energy. Do subscribe to the channel if you would like to learn a little bit more about your physics and hopefully improve your grades. Thank you.